So before we, where do I gotta put this down? So before we get into it, one quick announcement. We have next round of homeworks ready. I know a lot of you are still thinking about the current round, but if you're done with that or you're ready to get an idea of what's coming up, genetic algorithm and recommendations are the next two homework assignments. And of course, these assignments, no mutable state, no var, no importing mutable data structures and mutable objects, no shortcutting the system or getting around that. Banning mutability, so you're pushed into this functional programming style of writing, and we're going to start seeing more of that style, more of this functional programming approach. Especially Monday, we're gonna dive headfirst into a lot of different implications of being able to use first order functions in this language. So just a quick overview, genetic algorithm is the one so many of you have been waiting for. My TAs have been spreading the rumors around, and hopefully not scaring you too much about this one. I don't think it's too bad, but my TAs seem to think it's pretty difficult. I mean, it's not easy. But genetic algorithm, being able to our general goal of a genetic algorithm is to be able to solve problems without really solving the problems ourselves. So we want to apply some sort of machine learning, but not too sophisticated of an approach, not too complex either, because machine learning is a very difficult topic. But a genetic algorithm is sort of a glorified guess and check algorithm. So what we're going to do is give it some problem to solve in the form of a cost function and some way of randomly generating solutions, which we'll call an incubator function. With that incubator, the genetic algorithm is going to generate a lot of random solutions. The genetic algorithm you design is going to generate a lot of random solutions, test those solutions with the cost function, find the solutions with the lowest cost, take those solutions, throw away the rest, and then start mutating those and start searching in the areas of those best solutions, those least cost solutions, and also throwing in some more random solutions in there so we don't get caught in a local maximum. And then iterating many times until it slowly starts to optimize towards a fairly optimal solution for the problem that you're trying to solve. So it is an approximation algorithm, it's a randomized algorithm, and it helps us get a pretty close estimate of an optimal solution for a problem without actually having to solve the problem. We just have to generate the incubator. How does the genetic algorithm randomly generate solutions, potential solutions, which would do that using a list of doubles, and there's a lot of parallels to actual genetics and evolution, why it's called the genetic algorithm. We have a list of doubles that we call genes, forming an animal that are used to create an animal. The animal is a potential solution, and then we test that solution using the cost function, and we optimize based on that cost function. So implementing genetic algorithm, and genetic algorithm does have an expansion objective, and I feel compelled to tell you, not all expansion objectives are created equal. Some of them are going to be much more difficult than others. This one, I think, is fairly difficult, but worth it if you're interested in machine learning or AI. It's to use your genetic algorithm to train a neural network to be able to classify irises. So if you're interested in that field, if you're interested in the area, definitely go after this homework objective to be able to get that experience and kind of explore that realm of machine learning a little bit. It is not an easy homework extension. So if you're just trying to get one of them done and just trying to get the homework extension box checked, it's probably not the one to go for. Recommendations, I'm like 90% sure that we'll also have an expansion objective, but we haven't gotten that written up yet. We'll add that as time goes. So recommendations, given a data set is a big CSV file where I think it ended up being 475-ish customers and 35 items in a store. And for each customer, we get the quantity of each of those items that they've purchased. Given a new customer with no data, no purchase history known to us, and they're looking at a page for one of those 35 products, what products do we recommend that they purchase? what do we put on the recommended for that page? So we're going to look at all the data from all the other customers and look at which items customers frequently bought together. We're going to do that by computing the correlation between the items that were purchased. So given two items, what's the correlation between those? Did people often buy them together, not buy them together? Compute that. Using a lot of statistics, it'll be, the objectives are broken down into computing standard deviation of a set of doubles, or list of doubles rather, computing the correlation between two lists of doubles, taken by functions. There's functional programming in there. You have to read the doc for the specific details. And then the third one is the overall one. Given all of these properties of this data, which properties, which are the items that we're looking at, the items that we're considering, which properties have the highest correlations between each other? And then given one of those properties, what are the properties that are highest correlated with that one? So, and then the application is, given an item, which items are highest correlated with this item? Those are the ones we're going to recommend to the user. That's the kind of the high level of these. Of course, the details are in there in each of those documents. And they'll evolve a little bit over time, but I want to get them out there at least today. Recommendations, some of my wording I want to work on, rewrite the wording, but the objectives themselves aren't going to change. Those are going to stay the same, except possibly adding an expansion objective. We'll get the videos up, we'll get the GUIs ready. Certainly by Monday we'll have the GUIs ready for the pre-homework lab. So those are out there, ready for consumption. So take a look at those, at least definitely look at them early, just to at least get an idea of what you're in for with those. And start thinking about how you'll solve those without mutability. And recursion might come up in at least one of those. Of course it will. Okay, so any other questions, any last second questions before we get into this? And by the way, this feel free to ask questions. I mean, this always applies, but feel free to ask questions throughout. Recursion is one of those topics. Like I'll give my spiel. I'll show you what recursion is, but it's one of those things that just takes a while to really sink in, to get a feel for what is going on with this this recursion, because it can seem like magic at first. So so if you have questions, I'll try to go pretty slow today to just give you time for everything to sink in, everything to digest. And the first example we'll see isn't too complex. It's actually one we saw earlier in the semester. But I want to talk about the recursive side of this first algorithm that we'll see. The lecture question, we also saw this earlier in the semester. Given an integer, compute the prime factors of that integer. I made one change since we originally saw this question. The input 1 returns an empty list now. In the original, it returned a list containing only the value 1. I'm not positive why I did that in the original question, but it makes more sense to revert that. Plus, it makes the recursion a little easier without having that. Otherwise, it's the same question, except, of course, no mutability, no var, with the intention of writing a recursive solution for this, by restricting var to push you towards that recursive solution. The testing, there's no testing checked in Autolab, but you already have tests written for this. Just make sure you update your one edge case for the input of 1, making sure that that has empty lists instead of a list containing just the number 1. And you can reuse those tests. I already checked that you have these tests. We already had AutoGrader check for that. So I know you already have the tests. Just have those tests test your new implementation of this using recursion. So there's no reason for me to check your tests. I know your tests are fine because I already checked them in Autolab. Let's get into it. Let's talk about some examples of recursion. So this is the recursion we saw earlier in the semester where I kind of foreshadowed recursion, but I used this to talk about the stack. And we'll talk about the stack again today, and we'll see stack diagrams again today. But I rewrote this a little bit just to get rid of the var. There was a var in there, just the way I set it up. The only reason I used var last time is because I wanted one more variable on the stack, just so I could talk about the stack a little bit more. So now we definitely want to get rid of var. I'm not going to use var in my examples when I'm banning you from it. And that ended up compacting this code a little bit more. So let's go through this and focus on the recursive parts of this with the intent of being able to write recursive methods. Last time we saw this example, it was just walking through the stack and seeing how that worked and being able to trace through a recursive method. Now we want to focus on what about this structure do I need to understand to be able to write another recursive method. So with this, what we're trying to compute is the geometric sum. So the sum of all the values from n to 1. And I'm going to define my base cases. I'm going to define the behavior on 0 or any negative number just to return 0 for the geometric sum of 0 or a negative number, just in case some smart person calls my method with -6 or something like that. I don't want my program to crash. I don't want to go into infinite recursion or anything. So n less than or equal to 0 is just going to return 0. Other than that, I want n to return the geometric sum. So n equals 3. I want 3 plus 2 plus 1 for 6. That's what I want the output to be for this. And we verified last time that this does work, but we want to focus on the details of how this works. Why does this work? So let's take a look at our parts of our recursive method that we talked about last time. I'll talk about them in a little bit different order. Last time I said write your recursive case and then add in your base case later. That's why I'm talking about in a different order today for whatever reason. Our base case, this is always going to be some trivial input-output behavior. So what input for my method would just have really simple, trivial input-output behavior. If I have an input of 0 or negative, I'm going to return 0. Simple, and I kind of just made it up in part. Actually, I'm sure there is some mathematical definition for the geometric sum of zeros. Anybody know off the top of their heads? This is the geometric sum of 0. Is that defined? Okay. Anyway, so I'm just going to say it's 0. I'm going to make it up. I could have also done 1 returns 1. Maybe that would have made more sense in the mathematical sense. A base case of 1 always returns 1. And then I could have left 0 and negatives undefined. Maybe returned an error even or some -1, something like that. But the base case, it's always going to be trivial input. On what input do you just absolutely know the answer in such a way that it can't be wrong? It usually just returns a value directly. Something that cannot be wrong, or at least shouldn't be wrong, should be very easy to verify. If we didn't hit the if we didn't hit the base case, then we hit the recursive step. So anything that's not a base case is going to result in at least one recursive call. So if we hit the base case, good, just return the trivial answer. If the answer is not trivial, we're going to make a recursive call, and we're going to write our logic around that recursive call with the assumption that that recursive call is going to return the correct answer. So if I have compute geometric sum functioning properly, this method that I'm currently writing, I am not finished writing it yet at this point if I'm writing this, but I'm just going to assume that it's going to work. And then I'm going to base the rest of my logic based on that. So if I compute the geometric sum of n minus 1, how does that help me compute the geometric sum of n? Well, if I have the geometric sum of n minus 1 and I add n to it, I'm going to have the geometric sum of n. So I'm just going to assume that that's correct, that I will in fact get the geometric sum of n minus 1, add n to it, and return that. That's the geometric sum of n. So if my assumption is correct, then compute geometric sum of n is correct. So everything hinges on this being correct, which is the recursive definition. If this is correct, if compute geometric sum is correct, then compute geometric sum is correct. So we get this circular logic, which just doesn't really make sense. But that's what we're going with. If the method is correct, the method is correct. And then, critically important, this is I would argue the most important part of this whole design of a recursive algorithm is making sure that our recursive calls are getting closer to our base case. So here, if I have some input of n, it didn't hit my base case because I'm in the recursive step. Therefore, I know n is positive. If I make a recursive call of n minus 1, I know that I'm one step closer to an n of 0 to trigger my base case. I always have to get closer to that base case And when I say closer, I mean if I follow the chain of recursive calls, compute geometric sum of n minus 1, if that hits the recursive call, it's going to call compute geometric sum of n minus 2, then n minus 3, n minus 4. It's going to eventually hit the base case. Any recursive call has to eventually hit one of the base cases. We only have one here, that base case, but it has to hit a base case eventually. So it has to hit a case where it's not going to make another recursive call, or else we're going infinite. If you never hit the base case, you're always making another recursive call. You're going to fill up your stack with frames. You're going to get stack overflow. Program crashes. Nobody's happy. Nobody wants to see a program crash. So we have to get there eventually, and we know we're getting there. We start with some positive n. We decrement it by 1. If we do this enough times, we've had enough recursive calls, we're going to hit n equals 0. Hit our base case. That's going to return 0. And now, instead of adding more frames to the stack, we're finally going to destroy one of those frames off the stack, return a value, and then the next frame can start finishing up its call, destroy that frame, and start popping frames off of the stack instead of pushing more frames onto the stack. That's our goal, is to hit that base case and get rid of those frames so we can get on with the rest of the program, get out of the recursive call. So let's jump into the middle of the execution of this program. We walked through all the stack frames last time. I'll quickly get us caught up to where we are here. Then I want to talk about the recursive parts. Oh, and I guess I have to sum this up. But so if we're getting closer to the base case gives us something to grab onto and start returning, and kind of validates our assumption. And then if we designed everything right, then it just works, and that power of recursion kicks in and just gives us the right answer. Hopefully, either that or crashes, one of the two usually. So we're in the middle of this call. So how we got here, we called main. We started on line 10, started executing main one line at a time. Main got to line 11, called compute geometric sum, put that new frame on the stack for that call of compute geometric sum, and it's going to remember where it came from. I mentioned this last time, but I didn't visualize it. So let's put it explicitly right on the stack. Main is executing on line 11 and sitting right here waiting for this call to resolve, waiting for this stack frame to resolve and return a value so it can get on with its execution. This stack frame started here, checked the base case, n was 3, false, hit the recursive case, hit this recursive call of compute geometric sum, called that, put a new frame on the stack for that call, and execution moved to this stack frame, and this frame is remembering. I'm waiting on line 5, specifically waiting for compute geometric sum of n minus 1 to resolve, so it can get on with its execution. It wants that return value, so it can add n to it and then return that. This frame did the same thing. Base case was false. Hit the recursive case, put another frame on the stack, and we're sitting in this frame right now on line 5, about to make our next recursive call, which is finally going to hit the base case of our recursion. So we have all these frames on the stack, and we want to show how we got from that first call of 3 down to our base case, and then how we're going to get back up to that call of 3 to be able to return the correct value from this recursive method. So let's put that next frame on the stack. We have an input of n equals 0. And we're executing on line 1. We put the new frame on the stack. We're starting at the beginning of the method again and executing all the code for this method again, but in a different stack frame. So in this stack frame, we're going to look at line 1. We're going to check our conditional. That's going to be true finally. We're going to advance to line 3. We're going to find 0. This is the last expression of the method call. So we're going to return the value 0. So this is the first stack frame that actually gets to return a value. We're going to hit the end of the frame without making a recursive call. So we avoid our infinite recursion. And we're going to return 0 back up to the previous frame. Pop this frame off the stack, destroy that, go back to this frame with that compute geometric sum evaluating to 0. When we go back to this frame, we're going to look at where we left off. We left off at line 5, and specifically on this method call. of line 5. That method call, the frame for that call, returned 0. So now I can continue with my execution and I can run my logic. This is where we assumed that compute geometric sum was going to return the correct value. And then we're going to run the logic based on that assumption. In this case, compute geometric sum absolutely returned the right value because we hit the base case. So compute geometric sum hit the base case, returned 0, and now my assumption is of course true. I have 0, and I'm defining that to be the geometric sum of 0, and I'm going to add 1 to it, my current value event. I'm going to add that 1 to it. That's the rest of this method. That's the last expression. So I'm going to return 1 back to the frame that called this frame that created that one and put it on the stack. So I'm going to return 1 to this frame. This frame said my input was 2. Said my input was 2. I didn't hit the base case. So what am I going to do? I'm going to make a recursive call assuming that that's going to return the correct value. And I'm going to add 2 to that. So I'm going to call geometric sum of n minus 1 of 1 and add 2 to it, hoping that compute geometric sum was correct. We're going to assume that's correct. And now we can see that did return 1. So it was correct. That 1 came from a call of the base case, which was obviously correct. And then we ran our logic, added 1 to it. So we started with something that was obviously correct, ran our logic, adding the 1, returned that. Therefore, according to our logic of our method, that returned the correct value. So I got the correct value. My assumption is still true. This correctly computed compute geometric sum of 1. I'm going to add 2 to it, because that's going to be compute geometric sum of 2. And I'm going to return 3 back to this frame. This frame got the input of 3. Called compute geometric sum of 2, just assuming that that was going to return the correct value. And it did. It actually is going to return 3. It's going to add that 2 to 1, return that 3. I'm going to get that 3. I'm going to add it to the 3 that I have in n, compute that 6, and return that 6 back to the main method. Main method gets 6 from the return of all that recursion. We computed the correct value. We resume execution on line 11. We were waiting for this to resolve. That resolved to 6. I can store that in result and go on with the rest of the program. So we're assuming that our recursive calls are going to be correct. And that assumption becomes true when we start at the base case. The base case is correct. Get the return values from the base cases, run our logic. If our logic is sound, then that recursive call is going to take the base case returns, run the sound logic, and then return a correct value to another stack frame, which is going to get that correct value, run the logic, compute a correct value, return that back up the recursion, which is going to compute a correct value, return it up the recursion. So starting with our base case, our assumptions actually do become true when you start at the base case and think it's going from the base case and working upward. Where it seems like magic when you start at the top level recursion and work down. Well, we're just kind of making assumptions and it's crazy. You start at the base case and work up when you start seeing where that logic is actually flowing the way it should be and we're getting the correct answers out of this. Are there any questions on this example? I guarantee this will be the simplest example. This is about as simple as I can make a recursive example. I guarantee this will be the simplest one, so if there are any questions on this one, please ask them. Let's make sure we're all understanding this one before we dive back into anagrams, because that's what's next. all ready for anagrams. So right off the bat, I'm using a lot of functional programming syntax here. I had to get all the vars out of anagrams because I don't want to show vars on the screen during these 2 weeks. So I got all the vars out by using a lot of functional programming. It's not all going to make sense until we hit Monday's lecture. Then we'll really dive into it. I have a few slides at the end of today's lecture where I'll quickly describe what I have, some of the things I have on the screen here, the yield, map, flattened, and distinct. I'll talk about what those are. But for now, while we're talking about the recursive part of this, you just have to trust me that this does do what we expect it to do. And I'll revisit that. I'll talk about that when we talk about the recursive step again. What that was doing, in case you forgot from the last time we saw this one. So anagrams in a recursive method. We saw this earlier. I mean, it changed it to functional programming, so I still can't say you'll understand it today, but we'll at least get the recursive part of this, start understanding the recursive part. So the same parts are here. The same parts are going to be in any recursive method or algorithm or function, or whatever you're using recursion with, is we're going to have a base case, a recursive case, and our recursive calls are going to get us closer to the base case. Those are our ingredients. Mix all those ingredients together, you're going to have a good recursive method. So our base case here is an input of length 1. A string of length 1 is its own anagram. Just to recall the anagrams, given a string, give me a list of all of the ways that its letters can be rearranged to form new unique strings. That's what we want to compute. The base case of 1, if I have an input of length 1, I have a string with just one character in it. It is itself its only anagram. There's no other way you can rearrange a single letter. It just can't be done. So I have input. If the input's length 1, just return a new list, just containing that string. I'm already done. I already computed all the anagrams. Trivial input-output behavior. If that's your string, it is its only anagram. Just return it in a list. Done. There's nothing to think about there. Just return it. Done. Base case should always, I shouldn't say always because you can have pretty complex recursion. But for the most part, the base case should be a pretty simple input-output behavior. It should be something that's pretty easy to verify that is the correct behavior for that input. I do actually have an implicit second base case here. If you give this an empty string, it will return an empty list. So that happens in this loop. This loop iterates over the characters of the input string. Well, when there are no characters, this loop doesn't execute at all. And I end up, out of all this mess, I end up getting just an empty list. So I do have an implicit second base case there. I could make that explicit and say if length equals 0, return empty list. If length equals 1, return list of input. Else recursive step. I can make that explicit, but I don't know. I just didn't. And also notice, and this is often the case with recursion, is the base case is the only time I'm actually creating something. This is the only time where I actually create a brand new list. And then as we go back up the recursion from the base case, we're taking that list and appending more stuff to it. We're expanding this list until we have a list with all of the anagrams. But in those recursive calls, we actually don't create those lists. We're just taking the lists that were returned from the base case, appending letters to the values in those lists, combining those lists, and then returning those up the recursion, and combining more and more bigger and bigger lists as we go up. The same was true with the geometric sum. The base case was the only time where we really created a brand new int. It's the only time we created a new int. We created it 0, and that was where we started adding to it. We kept getting that 0 return, added 1 to it. Returned 1, added 2 to it. Returned 3, added 3 to it. The base case is where we're initializing stuff. And if we're thinking back to 115 with the accumulator pattern, the base case is like our initialization variable. If I want to sum all these values, I would set some accumulator to 0, iterate over some data, and then just keep summing all that data to that accumulator variable that I created until it has the sum of all those values. Same idea here, except it's in our base case where we're initializing the accumulator variable, if we want to think of it that way. What would be the result of that function call 3? I mean, in the previous example, this compute geometric sum of 3 returns 6. It's the main method. Got that return value of 6, put that in result, and then printed 6 to the screen. All right, so let's talk about the more interesting part here, the recursive step. So at least for now, unless you've studied ahead and learned some functional programming, you're going to have to take my word for it, because there's no expectation that you would do that by now. You have to take my word for it that this does do what we want it to do from the other times we saw this thing, and you can still see parts of our original code in here, is that this is going to iterate over the characters of the input string. And for each character, it's going to remove that from the input string to create this new string. We're going to remove just that one character. Then we're going to make the recursive call on anagrams on that string with that character removed. When we get that return, we're going to assume that's correct and base all of our logic on that being correct. And then append the character that we removed to the end of each string in that list. So each anagram in that smaller string, we're going to append that removed character to every single anagram of that smaller string. And then combine all of those lists for each of the characters we removed, append all of those lists together into one larger list, and return that one with the duplicates removed. So this is our recursive call. This is the one time we're making the recursive call. Anagrams is calling anagrams. We're going to assume that this is going to be accurate. We're going to assume this is correct, that this just returns the proper anagrams of the string that we give it, and base all our logic around that. So our logic was based around that, and our logic is sound. As long as anagrams of new string returns all the anagrams of new string, again, you'll have to take my word for it that all this functional syntax is doing what it's supposed to do, then our logic is sound, and we're going to get that proper behavior out of this. As long as, the next thing, as long as our base case, as long as we always reach our base case, that last part of our formula here. So since we'll have an input, we'll say it's of length n, and then we're always making our recursive calls on inputs of length n minus 1. So if we hit our recursive step, we're only ever calling anagrams on strings with one character removed from the input. So the length of new string has to be the length of the input minus 1. And my base cases are covered. Any length of 0 is going to be taken care of with this loop. Length of 1 is our base case. We can't have a negative length of a string. So I must have length 2 or greater if I hit the recursive call. If I ever made it to anagrams, this call right here, I have a length 2 or greater, and I'm going to subtract 1 from that before I make any recursive calls. So I'm always getting closer to a string of length 1 whenever I make a recursive call. So if I have a large string here, I'm going to say I have a string of length 10 anagrams. It's going to make 10 calls to anagrams with strings of length 9, and then 9 calls with strings of length 8, then strings of length 7, so on and so forth, until we finally hit our base case, which is going to return that list, append a character to it, return that, and then we can start returning back up the recursion and assembling all of our solutions into one large final set of all the solutions. So we have our base case, which sure looks correct. Our recursive case, with logic that's sound, assuming that anagrams of new string is going to return all the anagrams of that string. And we have our recursive call always getting closer to the base case. We got all the ingredients that we need for a successful recursion. And of course this one works. I wouldn't show you broken code up here. So that would be it. No, let's not do that. I have done broken code before as especially talking about testing. Like, okay, but this doesn't actually do what I said it does. Let's talk about it. But not today. So we always, I already talked about this. Oh, yeah, no, I didn't. Yeah, this is the next thing I want to talk about. So once our base case returns, that's when everything really starts going. Before that, we just started putting more frames on the stack, making more recursive calls, and not really getting anywhere until we hit the base case. We get a return value, and then we start assembling answers. We start returning back up the recursion. I did say that, didn't I? So it's at that second to last recursive call where we can start to see the mechanics of recursion working for us, where we can start dispelling a little bit of that magic. So say we're at some recursion, some level of this recursion where we have an input of length 2, we have the input at, and we're going to go through this loop and remove one letter at a time and make the recursive calls. So we're going to remove the letter A and make a recursive call, anagrams of the string T, and we're also going to remove T and make the recursive call on the string A. We're going to make those two recursive calls. Those both are just the base cases. So we're going to get those values back in lists. We're going to get two lists, one containing just A and one containing just T. When we get the list containing A, T was the character that was removed from that string. So we're going to append T to A, and we're going to append A to T from those two recursive calls. That's what we're going to do based on our assumption that this is going to return the correct values, which is correct in this case. We know that's correct because we hit our base cases on the recursive calls. So they're trivially correct. So we're going to append those values, and we have the total list of at and ta, which are the only two anagrams of this two-character string. So we get those two strings, and we return that. So our base case was trivially true, but if we go up one level above our base case to an input of length 2, we can run through all of our logic and see that, well, we are going to return the correct values in that input of length 2. And there were no assumptions here. I keep saying assumption, but I'm using that as kind of a placeholder. We didn't make any assumptions here. We just went through and saw, okay, we're going to make two calls to the base case. It's clearly going to return the correct values. We're going to run through our logic, and we ended up at the correct values, and we're going to return those. So now when we have that input of length 3 that just made 3 calls of inputs of length 2, and our inputs of length 2 are returning the correct values, well, guess what? That assumption we made is correct. Because we set everything up where our base case is true, our logic is sound, assuming that anagrams is going to be correct, and we're always getting closer to our base case. Since we had those 3 steps, our assumptions do end up being true. We end up getting the correct values returned up the recursion, and each step is going to actually have the correct values. We can do the same thing for length 3 and say, wow, any string of length 3 is going to return the correct value. That means our strings of length 4, when they made those calls of length 3, that assumption was correct. Those calls from 5 of length 4, that assumption was correct. And we can walk through our logic, starting with the base case and working up, and see that all our logic is going to make sure that those assumptions were actually correct. As long as we have those 3 pieces. We got closer to the base case was true, our logic was sound. We get there. Any questions on this one? We didn't use any variables there. We didn't add. We didn't change any. So when we go through, I didn't mention it, but this whole thing on the stack. None of those values on the stack ever updated. whenever we needed a new value stored, we ended up putting a new frame on the stack with that value. None of those, once n has a value, never changed. We just had a lot of different copies of n with different values. So we do kind of cheese the system a little bit, but that's what's pushing us towards this functional programming way of thinking, is being able to take advantage of the stack in this case to be able to kind of simulate a variable updating without actually creating a variable in the sense that it stores a value that can change. None of these values none of these n's changed its value, but we kind of get that behavior out of it without an actual value, or without an actual variable. All right, let's talk about some functional programming. No questions on that one? Besides the functional programming questions? All right, so threw some new words into this one. Let's talk about what they are. Starting with a brand new keyword, yield. This is a fun one. This can really help write your code and this will be true. You'll hear me say this a bunch on Monday too. But with functional programming, we can be very much more expressive about our code. Where with procedural programming, with object-oriented programming, we're often describing how our code does things. We'll have a loop. Okay, I need to initialize a variable. I need to iterate over this data. I need to do this logic inside of the loop, and then I'm going to return this value. It's very descriptive of what is happening. What is the code doing? With functional programming, it's more expressive of what it's. I meant to say how. The old style is the style that you're used to up until this point is how does my code work? Now it's what does my code do? It's more reads like English sentences, to be honest. So yield. Let's start with this one and just start talking about these. Yield is going to take a loop, in a sense, with this syntax of right after you start your loop, but before the body, put this keyword yield, and instead of executing the body of the loop, it'll still execute the body of the loop for each iteration, but instead of just executing the body of the loop, it's going to take the last expression that's evaluated in the body of the loop for each iteration of the loop and throw all those in a data structure. And it's going to try to match the type of the data structure that you're iterating over. I'm iterating over a range. It's going to try to put this in a range. It's going to be unsuccessful because my last expression is a list of strings. So it's not going to work. So I throw this toList on the end as well to convert whatever data structure it ends up giving me into a list so I can work in linked lists so we can motivate the linked list part of the course. But yield is going to give us a data structure based on a loop, based on the last expression that's evaluated at each iteration of the loop. It's going to collect all of those values from the last expression, put them in one data structure. I'm converting it to a list. The last expression was a list of strings, so I end up with a list of strings from my for loop. And I'm putting parentheses around this whole thing to get the toList, because yield is going to return that data structure, that whole data structure I want to convert to a list. And then store that in a value. Map is a very useful, very powerful method. This is much like your lecture question on Monday, this Monday, not next Monday, the one you already had, where you took a list and a function and returned a list with all the elements from the function, or all the elements from the list, but with that function applied to it in a new list. You were doing exactly what map does. Map is going to take a function, take all of the elements in this data structure, apply this function to it, and then whatever that function outputs for each element, that's going to be put into a new data structure of the same type, and that's what's going to be returned. The one new thing here, so this is a function. We could use the same function syntax that we saw the other day. I decided to use a little bit different syntax here, something Scala lets us do, is if we need a function that only takes one input and the type of that input can be inferred. So map is being called on a list of strings. So map is expecting a function that takes one input of type string. When that is the case, we can actually shortcut things a bit with this underscore notation. Instead of saying s of type string and then the big arrow, the equal, greater than, and then the body of my function, instead of writing all that, I can skip the whole first part, the whole parameter list, and just write the body of the function with an underscore in place of the input. So I don't have to name my input variable. I just pretend that the name of my input variable is underscore, and it can shorten my syntax quite a bit. So I'm saying take all of the strings in this list. So take each of those strings and do exactly what we want to do, is append that character that we pulled out of this original string, append that character to the end of all these strings.
Isn't that also like the symbol for like everything, kind of like how the star is in
Yeah.
JavaScript?
Yeah, it's kind of, it's like the wildcard operator. It just means something or anything. It's kind of a placeholder at times.
What is that? What's part of it?
So in this case, it can mean different things. So like if you say import functions._, you're importing everything from that package. So underscore can be like a star in other languages, where it means everything. In this case, we're using it as a placeholder to mean the name of the input variable of this function. So this is a shorthand to define a function that takes one input, and that input's name is underscore in this case. And this is special Scala syntax where we can say underscore, and Scala will be like, okay, you must mean this is a function that takes one string, because I'm expecting a function that takes one string. We can use this syntax to shorten that a little bit. So I'm pulling for each character, pulling that character out, creating a new string, making my recursive call. Whatever I get back, convert that list of all those strings to the same strings, but with that character appended to the end of it. And finally, these methods down here. Scala data structures have a lot of these functional style methods that just make our lives a bit easier. So before, this took a few lines of code to remove the duplicate values. And it could take quite a bit of code to take this list of strings and convert it to one list with all of the values from all of the lists. Well, Scala, I just take my list of strings. Flatten is going to convert that into a single list of strings with all of the values from all of the inner lists. It literally flattens this two-dimensional data structure into a one-dimensional data structure. And then distinct removes all the duplicates. Any duplicate values are gone after I call distinct. So you can start seeing we get a lot more done, and we can be a lot more expressive. Take the output, flatten it, and give me the distinct values in it. I'm not describing how my code does this. I'm just saying, hey code, do this. That's one of the features of a more functional approach, is our code is more expressive like that. So yeah, with that, have a good weekend. I'll see everyone Friday.